For today's lesson, we're going to be talking about nuclear decay. So through this lesson, we'll be discussing what happens to an element when it gives off radiation. Does it convert into something else? Does it just give off some energy? And then why do elements go through radioactive decay? Why do they give off radiation? Let's review our three types of particles that radiation is composed of. One is alpha, the second is beta, and the third was gamma. So remember, Rutherford did his experiment to discover those three particles. Let's look at the alpha particle. The alpha particle is the nucleus of a helium atom, a helium-4 atom actually. And so its size is very massive compared to the other two particles, over 7,000 times more massive than a beta particle. It has a charge of positive 2, because it is composed of 2 protons plus 2 neutrons, but neutrons don't have a charge. Its strength, it's 5 to 50 times more, has more energy than a beta particle. Outside of the body, it can be stopped very easily. So it can be stopped by a few centimeters of air, skin, plastic, cardboard. But if it were to get inside of your body, it has a very hard time escaping it. And so with that positive 2 charge, it can ionize a lot of cells and can do a lot of damage to tissues. And as we said before, it's composed of 2 protons, 2 neutrons. So we either write the symbol as a helium isotope symbol, so 4 for the mass number, 2 for the atomic number with He, or we write it with the alpha symbol, so the Greek letter alpha, 4/2 as well. Either way, however you would like to write it, but you'll see it both ways on your assignments. And it's usually given off by elements with the atomic numbers greater than 83. So elements that have that atomic number greater than 83 usually would give off some kind of alpha particle when they go through nuclear decay. So that's kind of a nice summary of the alpha particle. So our beta particle is a fast-moving electron. And so compared to the other particles, it has a negligible mass. So we consider its mass 0. It has a charge of -1 because we consider it almost like an electron. It has more penetrating power because they travel at very high velocities. So because they don't have very much mass, they can travel really fast compared to an alpha particle. So it can penetrate through a lot more material. If it gets inside your body, it's not as damaging to living tissue, again, because it doesn't have as much charge to it. So we can stop it. Again, it's more penetrating, so we can stop it with a few millimeters of aluminum foil compared to our alpha particles, which we could stop really easily with air. They're composed, again, of fast-moving electrons, and so because we consider a fast-moving electron, we use the symbol for the electron. So here it has an atomic number, which we put the charge down there, so atomic number of -1. It has no mass, so our mass number is 0, and then we use E for the symbol. Sometimes you'll see the beta symbol as well, but most often you'll see this symbol on your homework. And then our last particle, which is actually a ray. So gamma rays are high energy photons of light. And so they have no mass and they have no charge. But they are the most high, or the highest in energy. And so that because of this, they have the most penetrating power. So they can go through more things. But however, up close for an acute or short amount of time, they will cause the least amount of damage. Again, because they don't have that charge, it's really harder for it to ionize things. We can stop it with a thick sheet of lead or several feet of concrete. Again, they're a high energy photon, and so this is the symbol we use for a gamma ray. So 0 for its mass, 0 for its atomic number. Remember, it's just a light ray, and then the symbol for gamma, which looks kind of like a Y. What gives off gamma rays? So atoms, when they're radioactive, a lot of times they'll move electrons to an excited state. And so we call that a metastable state that it's in. So we use the M there to represent an element that's in a metastable state. And so here it would be what the symbol looks like. So 99M. So that M tells you that that atom is in an excited state. And so it has all this extra energy. So think of it like a kid that's on a bunch of sugar. So they're really high energy. So in order for it to come back to a more stable state and a more stable energy, it has to give off that extra energy. So you let the kid run around and, burn off that energy. So for an atom that's in an excited state, indicated by that M there, the metastable state, to give off that extra energy, it gives off a gamma ray. So here's kind of a summary of the ability for these different particles to penetrate through different materials. So alpha are very low energy, and so we can stop them with paper. But however, remember, if they get into your body, they are the most damaging to tissue. Beta and gammas are higher in energy. So beta we can block with some wood, gamma we can block with several feet of concrete. Because of their more penetrating power, sometimes they're considered a little more difficult to protect people from. But again, remember, alpha, if it gets inside your body, is the most damaging to tissue. So what makes an atom want to give off radiation? Why are atoms radioactive? And so it has to do with the ratio of how many protons to neutrons are in the atom. So if we think about the nucleus of an atom, all these positive charges are next to one another, and they want to pull apart. Okay, positive against another positive, they're going to want to repel one another. So the role of the neutron is to kind of separate those positive charges in the nucleus to make the atom more stable. Well, if there's too many protons and not enough neutrons, or too many neutrons and a little amount of protons, we'll sometimes get an unstable atom. And so this unstable atom, in order to become stable, will go through a nuclear decay process, releasing radiation. If you look at this chart, you can see we have the number of protons down here, the number of neutrons on our y-axis. And so if we have this band of stability here in blue, so this would tell us if our atom has, let's say, 60 protons and 80 neutrons, that falls within the band of stability. So it would be a stable atom. It wouldn't give off any radiation, or wouldn't be radioactive. But if it falls anywhere else on this graph, minus the island of stability up here as well, the atom would be unstable, so it would be radioactive. So it all has to do with how many protons to neutrons do we have in the nucleus. And so if we have an unstable combination, an atom is going to go through radioactive decay. So it's just going to give off extra energy, convert some of those protons to neutrons or neutrons to protons through the form of nuclear decay. Here you can see uranium-238 is an unstable atom, so it's radioactive. And it goes through this entire process to convert itself to a stable atom. So uranium goes through alpha decay, turns into thorium-234, goes through beta decay, turns into palladium-239, so on and so forth, all the way down until it gets to stable lead. So uranium-238, as it decays, which takes for uranium several thousand years to get down to this stable form of lead. So we're going to practice writing some of these nuclear equations, and here you can see an example. So radium turns into radon, gives off an alpha particle. So the key to balancing nuclear reactions or nuclear equations is to first know what are reactants and what are products. So reactants are things you start with. So those are always going to appear here on the left. The arrow then is going to point towards your products. Things you make in the end are things you give off, in this case for a nuclear equation. So to balance them, we want the sum of the atomic numbers on each side of our arrow to equal. So on this side, our atomic number is 88. Remember, your atomic number is the bottom number. So on this side, we also have to have a sum of 88. So 86 plus 2 gives us 88. We also want the sum of our mass numbers to equal. So here our mass numbers on top. So 226 on the left side of the arrow. 222 plus 4 gives us 226 on the right side. So the key to nuclear equations is to get numbers on top and bottom on both sides to be equal, or to sum to the same number. So alpha decay looks like this. So during alpha decay, or sometimes it's called alpha emission, we're going to give off that helium nucleus, or that alpha particle. So our atomic number for our element decreases by 2, so we go from 88 to 86. And our mass number decreases by 4. So we go from 222 to 218. beta decay, or beta emission, we're giving off our beta particle. So we can use the symbol for beta here, or our electron, which we'll most often use. So during beta emission, a neutron turns into a proton and an electron. And that proton stays in the nucleus, but the electron is ejected out at a very high speed. And that ejected proton is our beta particle. So if we look at our equation for a beta emission, or beta decay, we'll see that our atomic number on bottom goes up by 1, so it goes from 6 to 7. But our mass number stays the same, 14 and 14. That's because our electron has no mass. So let's try a couple examples here. So we want to write the appropriate symbol for the type of radiation given off by each of these reactions. So we have carbon-14 going through some type of decay, we don't know what, but it's turning into nitrogen. So let's figure out what particle that has to be. So we're going to just make sure our numbers on top and our numbers on bottom are equal on both sides. So we're starting with 14 for our mass number, and we're going to 14. So what plus 14 gives us 14? So our answer would be 0. Okay, so that should already tell us what particle we're looking at. Let's just double check our atomic number. So we have 6, and on this side we have 7. So we have to get them to both be 6. So 7 plus what gives us 6, and our answer would be a negative 1. So 7 plus a negative 1 gives us 6. So that would be our beta particle. Okay, let's try the next one. So we have 241 on top on that side, so we have to get to a total of 241 on this side, on the right. So we have 237 plus what is going to give us 241? And we would say 4. So 4 plus 237 gives us 241. Now let's check our atomic numbers. So we have 95 on this side. We have 93 on this side. So what plus 93 plus what gives us 95? And so we would say 2. And so 4 over 2 is our helium, or our alpha particle. So we could write it as 4 over 2 He, or we could write it 4 over 2 with our alpha symbol, however you'd like to write it. Okay, let's try a couple more examples. So for these ones, we want to complete these reactions representing the first 5 steps of the thorium-232 decay. We want to identify the missing elements A, B, C, D, and E. Again, for nuclear equations, we just want to make sure our atomic numbers and our mass numbers sum to the same thing on the left and right of the arrow. So for this example, our first one here, so we have 232 on the left side for our top number, so we have to sum to get that number as well. So what plus 4 gives us 232? And so we would say 228 plus 4 would give us 232. Now we got to get our bottom numbers to equal. So we have 90 on the left, and we only have 2 right now on the right. So 2 plus what gives us 90? So we would say 88. And now we need to know what element that is. So on the periodic table, we look for element number 88, which happens to be radium. So Ra. So for blank number A, we would put 228 over 88 radium. Let's try the next step. So here we got to figure out what B is. So on our left side, we have 226 on top. On our left, or on our right, we only have 0. So we know our top number has to be 226. Our bottom number, we have 88 for our atomic number. On this side, we have a negative 1. So negative 1 plus what gives us 88? And so we would say 89. And then we use our periodic table, look up what element 89 is. And element 89 happens to be actinium. So it would be AC. So our blank for B we would plug in 226 over 89 AC. Okay, let's try letter C. So here we have 228 on our left, 228 on our right. So we know we have to put in a 0 for our top number. Our bottom numbers, on our left we have 89, on our right we have 90. So 90 plus what is going to give us 89? And so we would say negative 1. Negative 1 plus a 90 gives us 89. So that would be our beta particle. So our answer for letter C would be 0 over negative 1e. Okay, let's try letter D. So again, we got to get our top numbers and our bottom numbers to equal on both sides of our arrows. So right now we have 4 plus 224 on our right. So that gives us a total of 228. Okay, now our bottom numbers, we have 2 and we have 88. So 88 plus 2 gives us 90. And then we use our periodic table to look up element 90. So element 90 is thorium. So we're back to a different version of thorium now. So our answer for D would be that. Okay, let's try E then. So on our right we have 224. On our left we have 224. So the blank for E has to have 0 on the top because they're already equal. Our bottom number, we have 88 on the left, 86 on the right. I think I might have typed that equation in wrong. But we would put in a negative, let's make that an 87. Nope, 89. So 89 plus what gives us 88? So we'd say negative 1. So our answer was E on that. Our beta particle, 0 over negative 1e. So again, we're just trying, our goal is to get the top numbers and the bottom numbers on both sides to sum to the same thing. Let's do 2 more examples. So we have radium-226, and it's going to go through alpha emission. We want to write the nuclear equation. So this time we got to write the whole equation ourselves. So we know radium we're starting with, so 226 Ra, and we need to use our periodic table to get the bottom number for our atomic number. So radium is 88. And it says we're going to go through alpha emission, so we want to write our alpha particle. So 4 over 2, you could do He, I'm going to use the alpha symbol. Okay, and we have to figure out what it turns into. So again, our top numbers and our bottom numbers need to equal. So 4 plus what gives us 226. So we would say it's 222. 2 plus what gives us 88. And we would say 86. So we need to look up what element 86 is. And 86 is radon. So that would be our nuclear equation for the alpha emission of radium-226. Okay, one more example. So here we have uranium-293, and it's going to undergo beta emission. We want to write the nuclear equation. So first step, write the element you're starting with. So we have 293 uranium, and we use the periodic table to get the bottom number, or the atomic number. So uranium is 92. Okay, and it's going to go through beta emission. So we got to give off our beta particle. So that's our electron. And now we have to get our top numbers and bottom numbers to sum to the same thing. So we only have 0 right now on the left, or on the right side. So we need to have 293 over here. Our bottom number, we have a negative 1. So negative 1 plus what gives us 92. So we would say 93. And then we use our periodic table to look up what is element 93. Element 93 is neptunium. So this would be our nuclear equation for the beta emission of uranium-293. So on your homework, you're going to get a little bit more practice writing these equations or filling in the blank.